back if you want to also edit it. Now, so that was, yesterday was kind of interesting actually. So we had 3 teams going, and it was actually a nice example of the 3D print cluster plus the other work happening at the same time. So we actually ended up redesigning the parts yesterday and printing them. And it turns out with 1.2 nozzles and 0.6 layer height, the individual prints only take like 2 hours once we optimized them and made them pretty small. So for example, the idler pieces, the motor pieces, all around like 2 hours. And how many do we have printed at this point? So yesterday we printed and tested some for the fit of the bearings and how they actually, the rods go in there. So it works. We can actually go into mass production on that. How many do we have already?
As of now, we have three of each. 3 idler, 3 motors, 3, and I started another 3 this morning.
Nice.
So
And that takes 6 hours for
no, for about 4 hours. Yeah.
4 hours each
Yeah, more or less. Yeah.
for 3 sets?
Yeah. Let me check.
Well, that's pretty.
3 hours
pretty rapid.
for the. What are these? These are the idler pieces, and then.
Huh.
We should have 8 wooden idlers as well. Isn't that where
you
we're making?
guys are getting idlers cranked out?
I thought that's
That's
what
what we were making.
Yeah.
Yeah, so I think we have
Yeah,
8
no.
completed wood
They're
idlers.
really not great, but
You already have 8?
Yeah,
I think so.
Really?
yeah.
So we can, if
Largely.
they work, we can, or maybe just keep the prints going, but
Keep them going.
keep them going and see which works. But go ahead. So you said like, what's the hour?
Yeah, about 4 hours. Yeah, around 4 hours
For 3 idlers.
for 3 idlers, 3 carriages, and 3 motor pieces. Yeah, it's about 4 hours. The longest one is 4 hours 15 minutes.
Wow.
Yeah, and it comes down. I mean, if you're printing with the 0.4 millimeter layer height, it's about 11 hours. When you change to 0.6, it comes down to 4.
Wow. How does that do that?
I don't know. It's incredible, yeah.
Well, yeah, because we're seeing them like pretty much come right up in front of our eyes. So that's actually a nice example of having that kind of prototyping happening at the same time. We're actually evolving the parts and using them. That's cool. So we can actually all start assembling axes then, like we talked about yesterday. So motor pieces, idlers, and then the carriages. Now, as far as how they fit.
Did you guys expanded the carriage slightly for the bearings?
Yeah.
Yeah, right on.
Yeah, we
And
modified
did
that.
you figure out kind of like how much more that needs to be because of the size of the bead? What was point?
Yeah, we did so yesterday we did the test prints
Just the
to
fuzzy
show
logic.
to show exactly what the print looks like for 1 inch and then for the 1.25 inch. So we oversized it. So we went to 1.1, which was a little excessive, but then if it's excessive, you can put a little bit of tape around the rod so they fit in easily. So right now we're not gonna have to fight
So
trying to
they
get
just
the
slide in.
Yeah, just slide right in. It's oversized. And then same for the other hole, so the bearings can go right in. And let's see, do I have any pictures? What's the latest pictures on that? But for the bearing part, well, that's all we can show, but that's pretty good on the frame. Let's just discuss the frame and then go into the axes detail, including how we're going to do this. Now, I'm actually hoping that's going to stand up in a workshop, because actually when you got that turn angle, man, I'm hoping we don't hit the ceiling. I think the ceiling is less than 9. Well, it's more than 9, but when you flip it,
I think we can do
You got
it just
this
in the
issue.
crest or right in the peak. I think we'll be able to do it right in the
Yeah.
peak.
Yeah, but this thing it's pretty nice. Now, this was challenging actually to get this at the end, and that's why. So this is the angle route of doing it. So this was kind of experimental in the sense that I would actually want to do this from 6 flat pieces, because the issue we run into, yes, you can make, the way we did it is we welded the 2 large sides So right there as it's sitting, you can call it the top and bottom. We welded that, but then you gotta fit the 4 legs in between those. So that's the challenge. The problem with that is, since this is pretty heavy weight, you gotta, you either need like 4 people to hold it up there for a bit of time as the person tacks the verticals into place. What we did instead was we did 2 verticals by laying this thing on the side. So, so we started by tacking in the 4 verticals. We laid it on the side so that we can actually put the other side, like, put it up, tilt it up. This is working with angle, and the challenge you're going to get into, and then we kind of tacked up, like welded up more. And as to be expected, we were fighting the last corner to make it go in because it was off by like 3 inches. So you had to use a clamp to get it right into place, which was kind of challenging because you don't have much to grab onto. We had to weld on one a tab and another like a ring, so when you put the vise on, the actual foot of the vise would not slip. So we actually welded a ring so you could put the foot of the vise clamp in it so it wouldn't slide, because it's hard.
You didn't have any ratchet straps?
Ratchet straps might do the job too.
You cranked it down in place.
You have to do it from 2 directions.
Yeah, of course.
So it's kind of challenging because one side is on the ground, so you got to lift it. That's just working with large weights. So after this experience confirmed that we want to do the same thing as the 6-sided frame method, which means you make the 6 sides. Each of the 6 are quite good because you can work them on a flat surface. And then you start with the bottom, you weld one side, you weld the second side, third side, fourth side. And they all have to line up because they're already rectangular.
Did you pull a 3-4-5 off of?
Yeah, we did.
You did?
We did. But the issue is once you tack it or start welding it, unless you're very careful, the thing shifts because the cooling weld pulls.
Yeah.
Like the weld is hot, it'll be somewhere, then it cools off, it pulls because it contracts. So you have to be careful about that. So,
So is the result now, is it now sitting flat on the floor, by the way, or is it a bit warped?
it's quite good. This is pretty flat on the floor, at least that side, and at least the 2 sides that were built on the floor are going to be pretty good, and the other ones, we'll see how they are. The most challenging in the result was, I guess, the top where, like the far side there, the top where we had to get it into place. I mean, we got it to it within like a 1/4 inch of the other sides, but there it might be off a little bit. If you look at it just visual inspection, you don't see that it's like all wonky. It looks relatively good. But just to review, how do you do the universal frame? Just to review, we went over this another time, but it's a good point to review now that we've got this other frame technique to add to our universal frame technique section. Uni. Different ways to make frames as far as all that we have done. So the largest is the rebar trusses. We've done one of these rebar trusses, and this is the kind of structure we're actually intending to build for the workshop. We built, now this is a 6-sided frame out of 1/2 inch by 4 inch steel for a heavier machine. That we did with a 6-sided frame method, and that works quite well.
How do you join the corners? This is flat iron.
Yeah, so you just weld the corners together. So it's flat iron, you just weld it.
You
So-
don't
But
cut,
aligning, I mean,
you
you
don't-
don't how you align it?
you don't cut the corners off.
No.
There's a
it's
square
on
piece
top.
that we added the
One on top of it.
So let's actually put this into this doc for how we want to do this in the future for a large scale frame, and how you minimize the cuts and the angles. Just do straight cuts, and we do what I call successive overlap. So let's take a look at what that looks like, but what's the pattern of the bars? So you cut, you can, and to make it simple conceptually as far as how you build it, cut one length only. You don't even need to worry about multiple lengths of bar. But how do you get the sides to be square? Well, you do this thing. Well, how do you, okay. So this is a question for you guys then. So tell me, how am I gonna get something that's got equal side lengths if I've got 4 equal size members? It's not gonna be like this, because one side's gonna be longer, so what do?
Connect the corners, corner to corner.
Could do that.
Oh yeah.
Successive overlap. I kind of call it, that's what I call it. But then now you got a square.
Okay.
That way you've got one part count for the entire frame. It's the bar
That's sweet.
that you cut to the same length. So this is the technique for large frames that I would prefer, because as long as you have this relatively decent, and you can pay attention to this, you can measure the cross, you can do it on a welding table so it's flat, you're starting with a flat, it's simple. This is designed for fabrication here. Large frame, this is what I would prefer for large frames. In fact, this is very good for the small frames too. Like, so let's go back in the frame dock here. What we typically did was with this was actually get these CNC cut. So okay, you're avoiding all kinds of inaccuracies. So this is once again a 6-sided frame method, and that's what it looks like. We did a bunch of nested frames so that we had better use of material. So we did a bunch of frames like that. If you're doing very large frames like this, like 6 by 6, 6 by 9, you're not going to get that out of CNC cuts because they don't make material that big. They do. You have up to 6 by 12 sheet steel. It's not super stock. It might be more expensive, but if you want anything larger, you can't do the CNC cuts. You do want to do strips. You can get strips standard lengths of 20 feet. So you can get 20 feet, so you can make a 20 by 20 by 20 frame using this technique, which we outline here, using this technique. This applies up to 20 by 20 by 20. From very small, like even the very small, if you don't want to go to you don't have a CNC cutter, you just take strip, thin bar, and do this thing. And it's quite precise, because you can pay attention. You can have a jig where you put in your 4 members and just line it up against the jig, and you've got pretty much perfect pieces. You just gotta make sure that when you tack weld, your welds aren't pulling. But if you're welding from the top, you're pulling it. You're not really pulling it. You're pulling it so it comes up off the table. Which, if you weld the other side, you can bang it down and make it straight again, and tack on the other side. So you can get pretty good quality control on this thing. So the other frames are the standard stuff, bolted, which the disadvantage of that is that the bolts take a lot of space and they're not usable because it's not a flat surface anymore, so you have to work around them. But you do get easy structures like this, like the first, well that wasn't the first, that's V2, or even the ironworker shears, the shear cutters like this, which we do from 1/2-inch tubing. So this ironworker right here, we took that could shear 1 by 10 steel.
Where was that?
Hmm?
Oh, that's here. Yeah, that is here.
Yeah, we did that in 2013 after we built the first ironworker, which took us 6 months, so we built this one in 2 days. So just to prove that you can reduce prototyping cycles from months to days by using modular design. This is just a very basic modular design using the frame, a bolted frame method. So using stock tubing. Here, doing a frame for could apply to a torch table or something like that. Once again, from the.
Were there any frailties to the cutting table? Oh, sorry, not the cutting table.
To this thing?
Yeah.
No, that worked. We took it to destructive testing up to 1 by 12 steel, and then the top bent.
Okay.
So we were testing it. Okay, how well can you do? So this is a thing you can replicate. The blade gap has to be pretty precise,
Yeah.
but you can get that because you've got flat pieces of steel that are bonding this thing together, so you can actually get a pretty precise blade gap and make good cuts. So here's you know, like a $40,000 machine for like $2,000 in materials. Continuing on the frames, and we got to add this new frame to this universal frame section here. And then we went to the 3D printed corners, which work effectively with angle. And that was the initial thought for this huge frame, but since we didn't have the printers up in time, we couldn't really print the corners, and the corners would have to be more than, I'm not sure they would fit for the 4x4 angle that they would fit on they wouldn't fit on a print bed. So we
But
couldn't
wood
really
block
do this.
would be as effective, right? Just a
Mhm.
block of wood. Instead of printing these angles, just a block of wood, or
Well, you gotta catch the frame, catch the angle with the angle slit. How are you gonna do that? Are you gonna mill that out or something?
okay, you need to slit. Okay.
Yeah, this thing has
Because of
the slits, which
Because of screws, or why is that?
no, you've got a complete slit like
Oh, that's the L shape, or okay.
How far into does the slit go?
yeah. Go look at frame corners.
Okay.
Four. Yeah. Just behind you.
Yeah, they've got a slit, so that's it's just a great way to hold everything together, and then when everything goes into the slits,
Okay.
it's guaranteed to be a cube.
Ah, okay.
No matter as long as all your members are the same length, you're
And they're
guaranteed.
printed square.
Mm-hmm. Yeah.
Say again?
And they're printed square.
Yeah, if they're printed
That's the
square.
assumption, of course.
Otherwise, it's no cube.
Right.
Just saying.
So if you go to the genealogy, the first time we used this kind of stuff was, let's see, I think maybe here, 2007. So if we go to the CAD, for example, you can pull up these corners. So that's how they look.
Ah, okay. Ah, that's different. Quite involved.
And we actually have a FreeCAD designer that you can design these, give it parameters so you can make this for whatever angle you like. We do have that designer within FreeCAD, so you can make custom versions of this. But it's a cool thing, and it would apply to this frame, but not structurally, because plastic is not going to hold this huge frame that weighs 500 pounds unless you print these very thick,
Very
which
thick.
you could. It'll just take you a bunch of material. So an effective way for these to work on a very large frame would be to use them as holders and then weld basically holders, basically a jig.
Just have kind of like an opening so that you can weld your connector.
Yeah, weld
Right,
like,
point.
you know, even like 3 pieces of rebar at every corner. That would get you a pretty solid connect, or just bars, like 3 bars at every corner. The holding is the tricky part because you're dealing with 500 pounds or so for that weight. So it gets pretty intense. These are the cutouts as on a CNC torch table. So those are the frame considerations. So here largely using steel, right? So this is all pretty much steel. And yeah, I would go to this in the next version because you know, yesterday was pretty tiring. This would be less tiring because you have to just put them up. Like the part that's tiring is like working the clamps and things that don't want to hold together, and you're working against steel. So you want to make it as simple as possible. So with that, that's okay. So now next step on this is to stand it up. Let's stand this up and let's mount the axes. And as mentioned yesterday, mount them at comfortable working height, not necessarily at the top because you're going to have to use a ladder or step stool.
How does the rod actually attach to the frame?
So let's look at the attachment. So that's the detail for today.
Because it might be easier to do it while it's laying down. I mean, not actually attach the rod, but depending on how it connects, it might
Yep.
be easier.
Yeah, it's true. You could do it. So there's first we do want to stand it up because
We should probably figure out where it should live too.
Mm-hmm. Yeah, like in the middle.
Because
I
when
think
we
in the
pull
middle.
this all together,
Totally
it's not
agree,
going
totally
anywhere.
agree.
Easily.
Actually, one more question about the frames. These 6 frames you're proposing, would
Yeah.
the material cost be a bit better if you know, just because of this flat stuff, or these the angles,
Yeah.
are they a lot more expensive, or it doesn't matter, or?
It's expensive, I would say, insofar as your labor, but steel is, when you go to stock steel, whether it's 1/4x4 angle or 1/4x4 flat, they're comparable pound by pound,
Okay.
so it will be the added labor cost. So let's take a look at our frame, which is somewhat like this. So what do we do first? We want to attach the z-axes first because they're the harder ones, or we can actually do all of them because they're actually on all 4 sides. So it's actually a very convenient structure to work as a group on the 4 at the same time. In fact, 6, because you got two Z's on one side, and there's enough space for people. There's 6 feet on each side, so you got actually comfortable working space for 6 teams if we had 6 teams. So that's axis attachment to frame. Well, so we've got your z-axes. First of all, like, what are we going to do for them? Where are they going to be? What kind of spacing? So where do we want to space them from the edge? We got, first of all, we've got 6 feet as the,
Should we break it
2
in,
feet?
in thirds?
yeah,
Does that
Good
make
idea.
sense? Or does it?
thirds is a good idea.
It should be pretty strong.
Although, should it be wider on the longer sides?
It's all 6 feet. Once
Well-
we stand it up, the only 9 foot is the height.
Yeah. So that.
So yeah,
actually
so
doesn't
we're-
bring-
So this is how we'd work it. Let's stand it up first. Because the other part about trying to work it on the ground, the axes would be fragile. You can damage them when you try to get this thing to stand up. So that's your 6 foot mark. So what's the center of the? So every third, so every 2 feet.
2 feet. Yeah.
So let's say 2 feet from the corner. Let's mark them, like halfway to the axis, something like that. So do that 2 feet, and yeah, basically 2 feet, or you can say 2 foot spacing.
2 feet on
And
side.
those axes just drives it up and down. The
Yeah.
bed is what actually goes side to side.
A bed goes up and down
Up and
only.
down.
The gantry goes up.
Okay, that goes up and down, and then there's movement on that axis. Okay, gotcha.
And let's discuss why that.
So that's the side view, right?
That's a front view, let's
Or
say.
front view, either way.
Yeah.
So it's always good to add it because, if someone has no context.
Get your computer out and add it.
Yeah,
Do you have a computer?
That's a fair statement.
So in collaborative design idea here, I'm not the only guy doing this. There's people contributing to this as I'm doing it. So that's the up. These are collaborative docs, meaning that anybody can edit this. The share permissions here are anyone on the internet can find and edit. So you can actually go into this doc and actually real time do this, including people remotely, because this is on the internet. So once again, I mean, all the design sessions we do, all that I do here is it's in live docs, so people can add pages and make. That's what we're supposed to do here in collaborative design. So that's the up direction. Now, where do we put? So we're gonna have. So these are how tall? They're 9. So we already cut the rods. We've got those. We can add the 9 foot dimension if we want.
We cut that on the press, yeah. Or did you cut
Abrasive
the
cut off.
Oh, abrasive
And I
cut
saw
off.
some were torched. The torched ends we gotta grind at. So include also the cut off ends too. They're sharp corners, so grind that down so it's actually safe to handle, so you can get cuts on it. So this side here, that's gonna be your 9 feet. Now, where exactly are we gonna mount the axis, which is gonna be 6 feet? Because we got 6-foot rods that are already cut to stock, the hollow tubes. So there's hollow and solid. So solid tubes vertically, solid tubes for Z, because that's only length we could get in the 9 foot. We cut it down from 20s.
I mean, they're attached into the up-down axis, right?
The XY, they're independent. The only thing, what does the Z axis attach to? The bed, just the bed. The X and Y are independent. The X and Y attach to each other, but they're independent from the Z. So that's not, I'm not drawing this correctly here. The Y and X, they're out here. Well, anywhere here. So that's going to be your, looking, say, that would be the two Y's, and the X connects in between them. How high? Let's just say comfortable working height at 6 feet, like we're like right there. So, because we can actually move this as we work everything out. It means that we can't print 9 feet, but all the mechanicals we can work out and all of that. So, just as we're building this, and we can easily attach it. But how do you attach it? Well, look at your. Let's look at the. Let's look at the 3D printed parts in the CAD. So we've got all this here. What's attaching? It's the motor piece, which is here. Let's just download this. Oh no, let's do the. So the motor piece, it's on GitLab because it's pretty large for some reason. You could clean it up and probably make it smaller. But so FreeCAD 16, I like to use legacy version, and then download the motor piece. It's on desktop. So open it up. So we need to attach the motor and idler.
And none of the motor or idler or any of these parts would be inside of the heat chamber. No,
Nope.
because they would all melt.
Yeah. This is all outside. The chamber is going to be the Z-axis. The bed rods are going to penetrate the heat chamber. Everything is completely outside of it. The closest to this in the open source is the Michigan Tech high temperature printer. Let's critique that. You can take a look at this, but these are good guys. The Joshua Pierce, he's like pretty hardcore open source hardware warrior. He actually ordered this printer for us for a build next year. So he's at university in Canada right now. The way they did their printer is they had a high temperature chamber, but they had the belt drive inside the high temperature chamber. It was like below the bed, but still that's not gonna get you too high up. You want to keep absolutely everything out, which we're doing. Other people use bellows or other means. Some people try to cool their motors. It's all complexities, just keep it simple, which is what we think we're doing here. On the motor piece, I took the idler piece, added tabs and put holes. This is like rapid prototyping. I took the idler piece, I enlarged the hole for the motor, and I put 4 holes for the motor bolt pattern. and that's it. That's what you see on the table over there. So, so this is what we're printing, Ken.
Yeah.
The bolt pattern of interest. And that's the bolt pattern of interest. All I did is, okay, it's in inches, but I did it in millimeters, and that was 47 millimeters is the number. So I just put 47 millimeters between the bolt holes here, and oh, now you see that the holes are offset. Okay, that's a bit of an error, but still works. What we got to pay attention to is that the pulley does not rub on the plastic, and I don't think it should, because I tested one, but the prints are coming up all on square, man. It's really bad. We should try to correct the axes. I'm not really seeing what's going on, because when I'm looking at the printer itself, the X and Y, like the bed and the Z they look relatively straight, but then the prints are not. Ken, any insights? That's a question
Yeah.
for Ben.
I'm gonna focus on it a little bit.
Yeah. But that's it. You got the rods going in. These are the 1-inch rods. I just butchered this thing. Like, this was, all I took was the old version. You see that's all egged out. I just said, okay, let me put in this larger 1-inch hole, because the holes here were too small and the spacing was different. So I just said, okay, let me put the spacing correct at 3.5. The rods still fit in there. Okay, just go with this, because we don't have time. So this holds your rods, it holds the motor, and it's good enough. So how do you attach it to the frame? Well, you've got these bolt holes on the outside. So I would suggest probably doing 4 bolt holes. So this is carrying quite a bit of weight.
Yeah, I was gonna
In fact,
say,
you
how
should
much
probably
weight
do
is this carrying?
a load. But the rods can be sitting on the ground.
I
So
get those ones are sitting on the ground, but not all of them are sitting on the ground, no?
well, for the
The other
X
ones
and
are
Y,
hollow,
we got hollow rods.
hollow ones.
So
No.
it's much better. It would
Much
be like,
lighter, but yeah.
but here we are talking about quite a bit of weight. But the rods are sitting, so all this is preventing is the rods like coming out. So I think if we pay attention that we don't like drop the weight of the rods on this, which we won't, because the rods are gonna fall through
Yeah.
to the ground. But then we can't move this, can't slide this thing on the ground.
Yeah.
We're gonna rip this thing right off.
Yes.
Okay. So as long as we do that, I think like 4 bolt holes on these corners, or even like do the ones which are more meaty, like in the middle, like do these 1, 2. Okay, so I'm pointing to these. Maybe do this one, that one, that one, that one, or even like this one and that one as a start, but probably 4. These are 1/4 inch, so
Okay.
I think 4 would be a good idea here.
Yeah.
Which ones do you guys like? You want to do these 4 corners on the outside, or what I just said?
Let's actually look at the.
Yeah.
the print.
Not much meat at the quarter, perhaps.
Yeah.
Right. This one here is like towards the center. Like as far as what we've got for amount of plastic, it's like these 4 in the middle look like the best ones to attach to right now. But yeah, that's all. So we have to transfer punch. You know, you can take this as a template, transfer punch into the frame, drill your holes in the frame. You can use a regular drill. You can use a mag drill too. I mean, a regular drill you have to push it really, really lean into it, but you can, because
Steel is soft. I mean, that's.
It's like butter.
well, you got to get your weight on
No,
it.
but
It's not
relatively
like wood.
No, I'm
relatively speaking,